Let's take a look at the term electrode-electrolyte interface. For that, consider a system like an electrode is immersed in an electrolyte or a solution. And we can consider this system as two separate phases like A and B. And the molecules in the nearby region of the point of contact between A and B and the molecules in the bulk region will have completely different environment. And just because of that, the force operating at this phase boundary are also different compared with the isotropic force in the bulk of the electrolyte. And the three-dimensional region of contact between these two phases A and B in which these molecules can interact with the molecules of both phases is called the interface region. And we can assume that it's only a few molecular diameter thickness. In general, we can regard it, this region as a transition region between the bulk forces. The term interface refers to the boundary surfaces separating the two phases. Basically, the presence of a new force at the interface region may disturb the isotropic properties. And due to the new forces near the interface or this electrode-electrolyte interface region, the arrangement of particles in the interface region is different. And then the ions and water molecules of the electrolyte solution may tend to adopt a new structural arrangement. And this also affects the phase on the other side of the phase boundary as well. Actually, the metal electrode surface consists of labile electrons, and these electrons can either move away or move towards the boundary, and which depends upon the excess charge on the solution side of the phase boundary. So that because of that movement of electrons from the electrode side, what will happen is a charge will be induced on the metal, and this charge will be equal and opposite to that on the electrolyte side of the phase boundary. So that after the creation of these charge pairs, a separation of charges takes place across the interface. That is a net charge of one sign, like this negative sign on the metal side and positive sign on the electrolyte side will be created. However, the interface regions as a whole is electrically neutral, and due to the charge separation, a potential difference will be developed across the interface. And this situation of interface constitute an electrical double layer or an electrified interface. Mentioned earlier, in a system of electrode-electrolyte interface, separation of charges takes place across the interface region where you will get one charge on the electrode side and another sign charge on the electrolytic side, and as a result of that charge separation, a potential difference will be created. Okay, so the excess charge on the metal electrode will create a preferential orientation of the water dipole or water molecules on the surface of the electrode, and the surface of the electrode will be occupied by a layer of solvent molecules. So there are two layers. The first layer is water layer or water molecules aligned to make a layer, and the second one is the solvent molecules from the electrolytic part. One condition is that ions from the solutions phase may approach the electrode surface only so far as their inner solution shells will be allowed, and these ions from the solvent side or the electrolytic side will occupy a layer which is very adjacent to the layer of the first water layer molecule on the surface of the electrode. And you can see that two layers, the first layer of water on the surface of the electrode and another layer of solvent molecules from the electrolytic side. And if you can draw a line through the center of that solvent molecules, you'll get a plane, and that plane is known as outer Helmholtz plane. So totally how many lines are here or planes are here? Two lines, like one water layer and another solvent layer. So both of these layer constitute an electrical double layer. The region in this plane constitutes the compact part of the double layer. Technically, in a simple case, the excess charge density on the outer Helmholtz plane will be equal and opposite to that on the metal. So totally there are two layers which constitute the electrical double layer, and these are all the important factors that behind the formation of a electrical double layer. In some cases, the ionic species which do not have that primary hydration layer that will remove the water molecules on the surface of electrode, and they themselves with contact absorb on the surface of the electrode. Usually it will happen in the case of certain anions and large sized cations, because they only can achieve this type of contact adsorption. So, in a system of electrode-electrolyte interface, an electrical double layer will be created at the interface of electrode and electrolyte. Like I said, like inner Helmholtz plane and outer Helmholtz plane, and a corresponding potential difference will be arised. If you want to get a relation between the charge density and the potential, we should understand the nature or the structure of the double layer. So there are many theories where came up to study the structure of double layer, and among that first one is Helmholtz-Perrin model. So in this model or in this theory, they said that in order to develop a potential difference, one phase must carry a positive charge and the other phase must carry negative charge at the phase boundary, as in the case of a charged condenser. So you can see that in the electrical double layer, the two layers, one charge is on side and the other side will be having another charge. So that positive and negative or negative and positive. So two different charges, and they are separated with a certain distance d. That means you can consider this system or this charge separation as a parallel plate or charged condenser. So these charge densities on the two layers are represented by Helmholtz as a parallel plate condenser, and hence this Helmholtz-Perrin model is also called parallel plate condenser model. And a potential difference again will be developed at this boundary, and that potential will be equal to V is equal to 4 pi dq by E or epsilon, where d is the distance between the two plates and epsilon is the electric constant or dielectric constant of the medium between the plates. Actually, in this model, the produced electric potential may move from its surface value to a zero value or the thickness of the layer. It depends upon the distance between the water layer and outer Helmholtz plane, or inner Helmholtz plane and outer Helmholtz plane. Anyway, a comparison of the theoretical predictions and experimental observations reveals that this Helmholtz model is not so satisfactorily explaining the structure of a double layer. That is, the electrified interface doesn't behave like a simple parallel plate condenser. Another one is Gouy-Chapman model or diffused charged model. In this theory, they suggested that the ions are under thermal motions, and thus they cannot be immobilized on the surface. The ions which neutralize the charge on the surface will spread on the surface of the electrode, forming a layer called diffused double layer. That's why their theory named as diffused charged model. That is, the excess charge density on the outer Helmholtz plane will not be equivalent to that on the electrode, but it will be a bit less. Some of the ions will leave their outer Helmholtz plane and randomly walk out into the solution, so that what will happen, the excess charge density on the solution will be decreased as per the distance from the electrode changes. So near the electrode, its charge will attract the solvent ions to the second row. That means the outer Helmholtz plane. But generally, the thermal motions of these ions are having a limited influence to focus from the electrode. Thus, the excess charge density in the solution will be or may not be fixed compact on the outer Helmholtz plane, but some of it is dispersed into the solution. Thus, most of the charges which neutralize that on the electrode will be held in the electrode between the outer Helmholtz plane and the bulk of the electrode. So that is the difference from the Helmholtz-Perrin model. In the Helmholtz-Perrin model, it was like the charges were fixed on the surface of electrode and the interface of the electrolyte. But in this Gouy-Chapman model, they say we cannot say that these ions are completely fixed or immobilized, but they are under thermal motions, and the excess charge density in the outer Helmholtz plane will not be exactly equal and opposite to that on the surface of the electrode. So next one is Stern model. The previously discussed Gouy-Chapman model and Helmholtz-Perrin model, both of them couldn't give a proper explanation about the double layer or electrical double layer. This is because the interfacial tension and capacity calculated from the Gouy-Chapman model and Helmholtz-Perrin model shows only a little agreement with the experimental values, because in Gouy-Chapman model they considered the ions as point charges. But in the case of Helmholtz-Perrin model, they consider the system as a rigid parallel plate condenser. So both of them couldn't give the proper explanation to the double layer, and it was another scientist, Stern, who gave a proper explanation to the double layer by combining the previous two theories, like a Helmholtz model and a Gouy-Chapman's model. And he tried to eliminate the point of diffused layer theory. So according to Stern model, part of the ions in the solution will stick on the electrode, forming a Helmholtz double layer, and the rest of the ions will diffuse into the solution, forming a diffused double layer. So you will see there will be two plane, like one plane is formed by the stuck ions on the surface of the electrode, and the other plane which is formed by the diffusion of ions. So what will happen is there will be another potential arise. Under all these conditions, the interface as a whole is electrically neutral, and the Stern charge Qs, you can see the equation Stern charge Qs, or you can explain this equation in another form, like the excess charge density in the solution will be the sum of the charge density in the Helmholtz plane plus the charge density in the Gouy-Chapman plane, or sometime you will see the excess charge density Qs is equal to the charge density in the Helmholtz plane QH plus the charge density QD, that is the charge density in the diffused layer. So the net charge density on the electrode will be equal to that of the charge density in the solution, and that is the sum of the charge density on the Helmholtz plane and the diffused double layer. So as per Stern model, we will get a concept of two distinct regions of charge separation through the interface. The first one is the interface region from the electrode to the Helmholtz plane. And the second one is the region from the Helmholtz plane to the solution across which the potential varies exponentially, attaining a value of 0 at some distance, or the Helmholtz plane to bulk of the solution, that is in general. And hence, we can expect two regions of potential drop as well. The first one is linear Helmholtz plane model and exponential Gouy-Chapman model. Using the same theory, we can calculate the capacitance in the two regions as well. That is the equation 1 by C is equal to 1 by CH plus 1 by CG. That is the capacitance in the interface region 1 by C will be the sum of the capacitance in the Helmholtz plane and the capacitance in the diffused layer, or the capacitance which is derived by the Gouy-Chapman's model. So although Stern model of the electrical double layer has been widely accepted, there are several limiting factors were there. One of the limitation is that it doesn't permit the calculation of properties of electrical double layer without recourse to the experimental data. Even then, too many constants in the theory render quantitative verification of the theory very difficult. So no account is taken of the dielectric saturation in the electrical double layer.